Here's the next basic part that we're going to talk about, where we're going to actually bring into the mix the discussion of linear acceleration. Right, we've already talked about how we can describe the movement of an object in terms of how far it's moved. We've talked about how we can describe it in terms of how fast it moves. Now we're going to talk about how that speed ends up changing, and that's going to be related to acceleration. So when speeds and velocities change, that means that we have an acceleration. That's pretty much the easy definition for it, right? The symbol A in this class is going to represent acceleration, and acceleration is defined as the rate at which an object's velocity changes. I wrote speed in here because you could also argue that if the speed changes, then we're going to have an acceleration. However, by definition, it's specifically the rate at which velocity is going to be changing. Now, one thing to keep in mind, acceleration and velocity are not the same thing. It might seem self-explanatory in that case, and you might think I'm just hitting hitting a dead horse at this point. But these do have two different connotations. However, a lot of times people tend to confuse them. A lot of times they think that just because we have a high velocity, that means we have to have a high acceleration. Or that if our velocity is pointing in a certain direction, that means my acceleration has to be pointing in the same direction. It's not. Uh, we can have maximum velocity and yet have a minimum amount of acceleration. We can have velocity pointed to the right while a acceleration is pointed to the left, or even in a completely different direction, like up or down. So acceleration and velocity are not the same thing. They may be related. Acceleration is related to velocity, but they aren't the same thing. The units that we have for acceleration are meters per second squared. So you should notice the pattern right now. So we have meters for position, meters per second for velocity, and now meters per second squared for acceleration. There are technically other types of variables that discuss the motion of an object beyond acceleration, and you can bet that the units will follow this pattern. There's a meters per cubed, meters per meters per second to the fourth power, meters per second to the third power. But we're not going to talk about that. As far as this class is concerned, acceleration is going to be constant. That means that the acceleration in this class is either going to be zero or it's going to be constant at some value. We're not going to really deal with cases where the acceleration changes, except for some very niche scenarios. There are some scenarios where you might have to conceptually understand what it means for the acceleration to be changing, but we're not really going to be dealing with a lot of mathematical problems like that. However, the APC, if you are preparing for that, that is something that they end up dealing with is changing accelerations. And that's actually where the calculus comes in. That's actually the reason why AP Physics 1 doesn't deal with changing accelerations is because in order to deal with them, you actually need calculus. So you need to be able to understand how to take a derivative or an integral. So if you're preparing for the APC, they actually deal with changing accelerations. It's honestly not that difficult. So do a few other practice questions, and you'll understand very quickly what those types of questions look like. All right. Now, acceleration is a vector, which means direction matters, right? The acceleration can be pointed in a certain direction. Now, what does it mean? What does it mean to have a certain direction for acceleration? Now, because direction matters, we could say that acceleration can either be positive or negative. When we say that an acceleration is positive, that usually means that the speed of the object is increasing specifically in the positive direction. So what this means is that the object is going to want to go positive. Now, if the object is already traveling in the positive direction, so it has a positive velocity, then a positive acceleration is going to say that it's going to keep going in that positive direction. However, if it has a velocity that's in the negative direction, then that actually would mean that the speed will end up decreasing as it becomes more positive. Now, this might not seem like it makes much sense, but it actually makes a lot more sense when you actually graph what's going on, right? So if we have a graph and we have our velocity, starting over here. So this is the velocity versus time graph, which we actually will do a little bit more in time. Then what we'll actually see is that if the object is increasing in speed in the positive direction, it's becoming more and more positive, it ends up having a positive acceleration. If it starts down here and it quote increases in the positive direction, the graph would end up looking like this. And you'll notice that both of these graphs end up looking the same. We can see that this graph is going into the positive direction, and as time goes on, it ends up switching over from the negative side into the positive side. So this is what we mean by it's increasing in the positive direction. The number is becoming more and more positive. So that's what a positive acceleration refers to. So we'll get rid of that. Uh, so if the velocity is positive, the object's going to speed up, and if the velocity is negative, it's going to slow down, and then reverse directions. Similarly, if we have a negative acceleration, it kind of means that the speed is going to end up decreasing in the positive direction. Or another way to put it, it's going to go into the negative. It's going to want to go more negative. So it's basically the opposite of what just happened. That if the velocity was initially positive and we have a negative acceleration, then the object is going to slow down until it eventually crosses over that line and becomes negative. Or if the velocity was negative, the object is going to keep speeding up in the negative direction. And again, we can see this in a graph that if the velocity was positive, or it would end up decreasing in the positive direction until it starts going negative. If the velocity was initially negative, it would decrease it would continue to increase in the negative direction with a graph that looks like it's going down. This is one thing to keep in mind is try not to get too confused with looking at this graph like in the eyes of a mathematician, where you think, oh, this graph is going down and it's decreasing, because it's not. Value wise, this graph is increasing in value, therefore it is speeding up. This line is slowing down and then speeding up after it passes this x-axis, because the value goes down, but then and then once it passes 0, the value starts going up. Right? Now, one thing, putting this all together to simplify what we just said is that if the velocity and acceleration are in opposite directions, then the object will end up slowing down. And if the acceleration and velocity are in the same, have the same sign, they're both positive or they're both negative, then the object will end up speeding up. Right? So this can help give us information about what's going on. If we know that the object is speeding up, or if we know that the object is slowing down, it gives us a hint as to the relative directions or relative signs of the velocity and the acceleration. So if we know what direction the object is moving and we know it's speeding up, we automatically know the direction of the acceleration and vice versa. Now, there's sort of two equations. There's actually really only one equation, but it can be represented in two different forms in order to find the acceleration. The way that I'm going to write it is this: v equals v naught plus at. So we have the final velocity equals the initial velocity plus acceleration time. Now, in your guided notes, you have a section where you can actually put the equations. So it has the number, I think it will probably end up having 1.3 there. So you have a little blank spot. That's where you're going to put the equation. And then on the side where you see this stuff, you're going to, in those spots, you can either write what those symbols represents, like how v represents the final velocity. So you can write that. However, I don't think that's super important because your reference table actually already uses those symbols and it defines what those symbols are. So that's not necessary. What you might want to do is use it to write down what the units are, because that's going to be a major thing to keep in mind, is being able to recognize what unit goes with what symbols and what measurements. It can help to really speed up the process of reading a question and pulling out the important information. So if you kind of have a handle of, okay, this is going to be meters per second squared as a reminder, this is going to be in seconds, then when you read a problem, anytime you see meters per second, your mind should go, it's acceleration, it's A, and you can kind of continue on from there. All right, so here's the first question. Pause the video, work self, and we'll go over in a second. All right, so we have a car being driven south, and they want us to figure out what the direction of the car's acceleration. Because they tell us that the car has decreasing speed, that means that the velocity and the acceleration are in opposite directions. So the south means that the opposite of south would be north, so the car's acceleration is going to be north. All right, here's the next one. Pause the video, work self, and we'll go over in a second. All right, So they want us to calculate the magnitude and direction of the acceleration. So we're going to take the numbers and plug it into the calculator. Now we do need to be careful. So when we go to write down our given pieces of information, we go through this. We know that the initial velocity of the object is going to be 3 meters per second, and then the final speed is going to be 2.8 meters per second, and the time's 2 seconds. But we have to be careful because the v's in that equation represents velocity. And again, with velocity, direction matters. So if they're moving in the same direction, I leave them as the same sign. But once I start changing direction, I have to note that one of them is in a different direction by making it negative. And here, when the ball rolls towards the wall and then bounces back off the wall, that basically tells me that the ball goes from moving in this direction to moving in this direction. So of these two velocities, one of them has to be negative. It doesn't really matter which one, as long as I'm being consistent. So I can make the 2.8 negative and just remind myself that away from the wall is defined as negative. So let me just clear this before I start pulling stuff. So that's what I did here. So the initial velocity is going to be 3. The final velocity is going to be negative 2.8. When we plug these two numbers in, we end up getting the answer negative 2.9 meters per second squared, which tells me that the acceleration is 2.9 meters per second squared away from the wall, because this sign and this sign are together, which means that the velocity that points away is in the same direction as the acceleration that points away. Right? And that's basically it.